So the next is have an alternate is to discuss an alternate form for the ripple factor. This is nothing but a rearrangement of this equation, the basic definition of the ripple factor, and this equation. So the next performance parameter that we are going to discuss is the transformer utilization factor, or TUF. It is defined as the ratio of DC output power to the Vs over Is, whereas Vs and Is are the secondary side voltages and the current of the transformer. Here we have this Vs and the diode and load. Vs and Is are the RMS voltages of the secondary side of the transformer. The secondary side current of the transformer will be equal to the load current. The next we have is displacement angle phi. This is the angle between the fundamental component of the current and the voltage Vs, and the cause of this displacement angle is known as displacement factor. Next we have is harmonic factor. So we have considered that the current drawn the current at the input side is a square wave, which means that it has infinite number of harmonics in it. The first harmonic IS1 will be is this the fundamental harmonic IS1 is this, and Is is the input current, RMS value of the input current. So the difference of the square of the Is square minus Is1 square divided by Is1 whole square, and its under root will be is defined as the harmonic factor. The next is power factor. Again, the definition for the Is1 and Is remains the same. That is the fundamental component of the current, input current, and the RMS value of the input current. The fundamental component is I is equal to Im sine of omega t. The second, third, fourth, fifth, and so on will be 2 omega, 3 omega, 4 omega, 5 omega, 7 omega. Only the frequency, the omega frequency will keep on increasing from omega to 2 omega, 3 omega, 4 omega, 5 omega. So it is desirable to have the maximum amount of our power content in the first component of our signal. So that's it. Now the next is the crest factor, CF. It is the ratio between the Is peak to Is. It is the measure of the peak input current as compared with its RMS value. It may be useful in finding the peak current ratings of the devices. Next, we are going to discuss the example in which we have to determine all the factors that we have previously discussed. So we have this transformer, and a rectifier circuit is here. A diode D1 is connected, and a load R across which the voltage is V0. The first is to determine the average voltage VDC. Average voltage, average value we know that can be calculated by integrating the quantity or its time period. The average DC output voltage is only available from 0 to pi, that is half cycle. When integrated over its half time period, the value that we obtain is something like this, and Now if we put the values of this omega in terms of this time period t, what do we have is frequency is equal to 1 volta and omega is equal to 2 pi f. So this omega, instead of that we will put these values over there. The value that we obtain is Vm over pi. This is the average or the DC value of the voltage waveform or that we will obtain at our output. And remember that this is only valid, this formula is only valid for half wave rectifier. In case of full wave rectifier or in other topologies, we will see that since the time of conduction of this diode and this output voltage available will be different. For example, in case of full wave rectifier, we will see that the output is available from 0 to pi and from pi to 2 pi as well. So for that, the average value obtained at output will be obviously different. And IDC is nothing but VDC divided by its resistance or the load R. Next is to determine the RMS value. RMS value is nothing but integration of the quantity, not the quantity but the square of the quantity over its time period. So the result that we obtain after solving this simple integral is 0.5 Vm, and similarly IRMS is nothing but VRMS over R, which turns out to be 0.5 Vm over R. Now these two values we have calculated VRMS, IRMS and VDC and IDC in order to calculate the efficiency. We have discussed in the basic definitions of these quantities that efficiency is PDC divided by PAC. A ratio of PDC to PAC is efficiency. So both PDC is equal to VDC into IDC and PAC is equal to VRMS into IRMS. We have the values of PDC, IDC, VRMS and IRMS, on the basis of which we have calculated PDC and PAC, and the efficiency in case of half wave rectifier turns out to be 40.5%. The next is form factor. Form factor can also be calculated using its definition, which is VRMS over VDC. This is very simple and turns out to be 157%. Similarly, ripple factor can be calculated as square root of form factor square minus 1, which is equal to 121%. The next is to determine the transformer utilization factor. So its RMS value is Vm sin omega t whole square integrated from time for its time period 0 to t. See that the time period for this one will be different from the DC for the waveform that we obtained for our output DC voltage. It was operating for 0 to pi, and in this case it will be operating for this is the transformer output voltage that will be available throughout the cycle. So in this case the voltage VRMS comes out to be 0.707, and similarly the load the current on the secondary side, RMS value of the secondary side of the transformer is equal to the load current. Since the load is in series with the transformer, and whatever the load will be drawing, it will whatever the value of current the load will be drawing, it will be supplied from the secondary side of the transformer. So that's why both the I load and I S RMS are same. So the total utilization factor formula is